part, all the reduction formula is one side is that you understand how the computers actually handle that kind of problem. If I put x to the n to the cosine x, how it's going to actually compute it. Maybe it's going to use this type of recursive formula. So we understand the idea behind it. This is the more theoretical side. Is actually pretty darn important for Calc 2, the idea of use of reduction. All right, so let's try this one. It's very interesting. I say it's also very important application. So what's a little bit different about this one? It shouldn't be called reduction, if you have noticed it, right? Why shouldn't it be called reduction? You see which one is integrated and which one is differentiated there? Right? Yeah? That is exactly right. Before, we just try to knock that down to make it smaller power so that we can just get to e to the x, right? But it was bumping up. Another thing is that they didn't just integrate x to the n. They're playing with a slightly linear version, 1 minus x to the n, right? So it's not easy to explain why 1 minus x to the n. They manipulated it and realized that this is the right one to get to the answer really cleanly, but they don't discover things like this. Another thing is that if you, instead of doing, x to the n, if you flip the sign x to 1 minus x to the n, the sign in that integration by part becomes a positive. Right? So the formula is a little bit cleaner. You don't have to deal with the sign changing all the time, every time you do that. There's two reasons. So let's think about antiderivative of 1 minus x to the n first. What do you think? Now you do u substitution, right? U to the n. And du dx is pretty simple, right? What is it? -1. So do you think you can do that in your head? So will there be some sort of n plus 1 power there? Yes or no, right? And what's in there? U is exactly that. And what's in the denominator? Negative and n plus 1. Right? That's actually antiderivative. Does that make sense? All right, but this is not indefinite integral. This is definite integral, right? So you have to evaluate at 0 and 1. So can you go in and actually complete this one? Apply integration by part to integrating this part first, then differentiate, and try to clean up things like this so that you have a clean formula about an and the bn. Okay, and then we're going to actually do this one by hand. There's a point to this. So the thing that we just did with the computer, we're going to do that by hand. But that's our first exercise today. Is that right? Compute an and bn. Number 2, exercise number 2. Right, was that okay? So we already did that antiderivative of 1 minus x to the n, so I copied it here. So that's copied it. When e to the x is differentiated, nothing happens. Let's go in there. If I evaluate the 0 and 1, you notice that this 1 minus 1, when you plug it in, cancels. So that's why they chose it. That's actually the secret choice in there. Its integral is going from 0 to 1, and they chose the 1 minus x to the n, so that first evaluation at top limit becomes 0. So the negative becomes a positive as you subtract it off. All right? So that choice 1, inside choice 1, is actually because of that reason. So if this is in general b, and that's going to be b minus x. So that when you evaluate the 0 to b, the first term is always 0 because of b minus b, and it picks up this one there. So that's a little setup at linear, so they can pull out what they want. They probably discovered a lot longer period, but here's a shortened version. So we got this one. Agree? The first one is 1 over n plus 1, the coefficient of this one. And after you do that, this one looks a lot like it, very clean. Everything is the same except that one exponent, correct? Yeah. And I'd like to claim that the name for this one is not fnx is not a good name for this. Can somebody explain why fnx is not a good name for this one? No, that's not. If this is fn x, this will be fn plus x. Yeah, but fnx is not a good notation for this one. Just kn maybe is a good notation. I just dropped x. There's no parenthesis x in there, and I hope you understand why. Understand why? Because the definite integral, if you integral from 0 to 1, what is it? Some number, right? There's no x in it anymore, but it does depend on that n, correct? Just like that advanced problem that is due tomorrow, right? If you look at that advanced problem, it's just like that. Jn is defined just like this. It's a number only depending on n, there's no x in it. All right? So that's kn, and what is this one? Kn plus 1. So we have a pretty simple system of recursive formula on numbers. That's what we entered. But this does something pretty amazing. Right? It's a eureka moment we are about to enter in here. So to do this one, interesting thing is that we're going up. We're not going down. Right? That's another interesting part. What is K0? Can somebody calculate K0? Now that's our definition of Kn. Right? What is K0? You go ahead and plug in n equals 0. So that becomes 1, right? So this integral from where to where? 0 to 1 of what function now? E to the x and dx. And who knows the answer? E to the first minus e to the 0, which is 1. That's what K0 is. We're going to go to K1 and K2 and so on. All right? So let me write them down clearly that this is a formula, Kn equals 1 over n plus 1, 1 over n plus 1, multiplied by next item, Kn plus 1. Okay? That's a recursive formula. All right. So that's the rule that'll determine infinitely many numbers starting from right here, e minus 1. So K0, that is e minus 1, is now let's apply it here. It goes like this. If you see the 0 down there, the n, in the right-hand side, every index is a 1 index higher. So if you see 0, you see 1 over 1 plus 1 over 1, K1. Fair enough? The 0 in every index here is 1 more. So this is 1 plus K1. Okay? You continue, it's still K0. Still K0 is 1 plus. What can you do about the K1? You apply this one again, right? That's the idea. K1, if it is K1, all the right-hand index is a 2, 2, 2, right? So it's 1 half K2. Does that make sense? Okay, so let's expand this. 1 plus 1 half and 1 half K2. I'll do one more time until you pick up the pattern. 1 half is there. So let's see. Let's replace this K2. How do we replace the K2? K2 with the 3, 3, 3 in there, right? So it's 1/3 K3. Fair enough? So that's going to be 1 plus 1 half times 2 times 3 plus 2 times 3 K3. I'll do just 2 more times and everybody will understand what this one's about. So let's do 2 more times. 1 half is a 2 times 3 plus 1 over 2 times 3. What's K3? 1/4 plus 1/4 K4. Correct? So let's expand that. 1 plus 1 half plus 1 over 2 times 3 plus 1 over 2 times 3 times 4 plus 1 over 2 times 3 times 4 times K equals 4. So I hope you now pick up the pattern. Okay, that's going to go forever like that. So let's write that down. Maybe we can just write it as K0 is a 1 plus 1 half. Does anybody know the better notation for 1, 2 times 3 times 4 and 2 times 3 times 4 times 5 and those things? The factorial notation. So that's a shorthand notation. That appears a lot in many differential equation and solutions of a differential equation and things like that. So we're going to write this one 3 factorial. It's an exclamation mark. It means 1 times 2 times 3. And this one will be 1 times 2 times 3 times 4 is a 4 factorial. Right? And then plus 1 over 4 factorial K4. Like that. But let's just go on and see if you can write down how the n shape look like. If you reach the end, 1 over n factorial, and you can see right next to it is exactly the same number, right? So it's 1 over n factorial kn. That's how it ends. Okay? So what is the k0? Yes, go ahead.
Wouldn't the previous term be 1 over n minus 1 factorial?
No, this number here, n factorial and 4 factorial, and that 4, they're all the same. So it does, you can do that. It's n minus 1 factorial, n minus 1 factorial, kn minus 1. That's fine. But you have to keep it all in the same letter. Is that good? So what is k0? Anybody remember k0? It was e minus 1, right? So here's the moment. Not yet, but it's almost. E is 1 plus 1 plus 2 factorial, which is 1 times 2 is the same as 2, right? And 1 3 factorial. 4 factorial, go all the way up to n factorial. This is pretty good. N factorial is pretty good. And then this later term n factorial. And who remembers about kn? The definition of the very definition. That involves integral, right? From 0 to 1 to 1 minus x raised to the, is that n plus 1 or just n? I think it's n plus 1 e to the x. Thank you. That's right. No, it was n plus 1. No, kn is the n. Right? Kn plus 1 is n plus 1. So kn is the n. So n here is exactly the same. So it turns out this is a negligible term. That means this quantity depends on n, right? And this one approaches 0 as n approaches infinity. So if this n is 2015, can you imagine 2015 factorial? That's a huge number. Multiplying 1 through all 2015, that's amazing. It's a huge number. And when you reach that, this integral is, I'm claiming, is very, very small. Right? So if you believe that, then e is almost equal to that. So here, let me summarize what just happened. E is in that shape. I think I'm doing wrong with this n plus 1. This should be exactly n and n the same as we worked out, because at the end we arrive in that shape, always the same. But and I was claiming that this one with the integral is a negligible term, so if you keep going, that e is going to be some of the reciprocals of the factorial numbers. So here's the left-hand side, very well-known irrational number, right? Why is the irrational number called irrational? Because if you look at the decimal digits, there is no repeating block of patterns, right? But this one is not repeating block, but there's some sort of pattern is revealed by the simple game. Right-hand side, 1 over k factorial, these individual things, is very simple irrational numbers. And there's a clear pattern revealed is involved in this unfolding this number. Before, no pattern in terms of blocks of digits. But if you look at it this way, there's clearly a pattern. So irrational number, that irrational number can be called some sort of rational, some patterns in there. So that's amazing, right? By just doing the integration by part, a couple of times you discovered the secret behind this mysterious number. It doesn't stop. It'll tell you how the pi's unfold. It'll tell you how the cosine 2 radians is calculated with your calculator, and how calculator computes the sine inverse of 1/3, and how they compute the log, all the thing. How do they get that old table? Is because they realize that all of this quantity I wrote down has this secret behind it, and we can reach that by doing this business multiple times, right? So all those transcendental functions reveals this secret behind it. sine and e to the x and log and cosine x. So this is a pretty simple application actually of integration by part, but its consequence is amazingly powerful. All your calculated number table to a arbitrary precision is built using this machinery. All right?
Which came first? The numbers? Like pi come first? Did e come first? Or did
They
they
didn't know this. Pi was there as a proportionality in terms of circumference and the ratio, I mean radius, and they later discover how the pi and e looks like this one using this function analogy. They didn't know this one before when the pi was invented. So the power of that reduction formula backward, and that's that's behind the secret of computing all these numbers. So in general, that technique, actually you can apply that to anything in here. This is the shape, and this is if you apply exactly the same thing, you got a similar formula, and it can be replaced with a b, not just one. And if you apply integration by part, you arrive at here, do exactly the same thing, call that one kn and k minus 1. If you repeat it, you discover the formula. So I'm just going to show you how the formula looks like. It's because it's complicated. It's probably difficult to understand what goes in there, but this is a part that correspond to no matter what your function is, e to the x part replaced with the cosine and sine, tangent inverse, all that. And if you can compute the kth derivative at the 0 point, and this is something you can easily compute, and you have to show that this part is actually negligible, then you show actually these two things are almost equal. Therefore, it's a good approximation. All right. So this is the most powerful and important application of actually calculus 2. Physics part and geometry volume. What is the rest of the part is about? Pretty much about this one. But the entire formula is already available just simply using the integration by parts. So I'll explain a little bit more about that 1 over e because there's a part that's left over a little bit. So I was saying this part, if this guy goes to 0, and remaining this clean number, right, very clear pattern, is almost e. But it remains to show that why is this one is approaching 0, right? So here is the estimation. Typical analysis. If you want to show something as a 0, best way is to put the absolute value and show that it's a 0. So they usually approach it like this. We're going to consider this one n factorial integral 0 to 1 minus x raised to nth power, e to the x and dx. We're not going to calculate this one exactly, but we're going to replace this one as a larger number. Not too big, but it's good enough so that we can conclude it. So this is not equal, but it is less than. 1 over factorial, that's a positive number that can go outside. This integral is really the sum, right? So let me ask you this question. If I add everything first, compare with, I put absolute value around and compare these two things. Is there an absolute direction of inequality, or is it depending on A and B and C? Or is there some directions? Absolutely. You add all that and absolute value later. Absolute value first, change everything to positive and add them later. Which one's bigger? Definitely this guy is bigger, right? If they're all positive, it's the same. If there's ever a negative number, this will be the bigger. But that's what this really Riemann sum is about, right? Putting the absolute value later versus, and Riemann sum is really adding them up. So you can compare that with, okay, let me sum later after you actually put the Riemann sum in there, I mean absolute value there. Then it gets bigger in general, correct? But these are all positive numbers, so it doesn't matter, but in general you have to approach it like this. All right, then there's x in it. So how are we going to get rid of x in it and make this integral simpler is replace with a maximum value. Okay, maximum value. If x varies from 0 to 1, how does 1 minus x vary? If you look at the graph, it varies from 0 to 1. When x equals 0 is 1, right? When x reaches 1, it becomes 0. So straight going down from 1 to 0. So it varies from 0 to 1, right? What is the maximum there? 1. So I'm going to replace this one. Again, is not equal. Replace it with the maximum, which is 1 raised to the nth power. How about e to the x? What is the maximum value between 0 and 1? X reaches 1. So if I replace x with 1, then it is always larger. So this integral, if you compute this with this maximum value, this is always larger. This is like integrating this one versus integrating with the horizontal line. Of course, horizontal line integral is the big thing, right? And the actual function is below it. So this one, the actual function we don't care about, this one is actually bigger and is good enough to conclude whatever we want to conclude. So this inequalities, this one is horizontal line, there's no x in it, area underneath it. This one is the actual area underneath it. Of course, this one is bigger because this horizontal line is above everything. So does this make sense? Inequality is not equal. So what is this one in here? There's no x in it. So 1 to the n, it's just 1. So it's 1 over n factorial. And this is 0 to 1 dx. This is simply just 1, right? So what I've showed here, this thing, difficult to calculate exactly, but I just show that following this chain of inequality show that it is always less than 1 over n factorial. Alright? So this quantity we don't know, but it is less than 1 over n factorial. Well, it's just absolute value is always greater than or equal to 0, right? So what happens as n approaches infinity to the 1 over n factorial? Is the symbol is tricking you? This is 1 times, 2 times, 3 times, all the way up to n, right? If n approaches infinity, you can imagine how big this is going to be in the denominator. Approaches 0. So what happens to that guy? What is the theorem that allows you to conclude that middle one is a 0? Sandwich theorem. But in my book it says squeeze theorem. But that's I like sandwich theorem. But I know squeeze theorem. It both starts with S though. Squeeze theorem. So we conclude that one goes to 0. That part at the end is negligible, is proved. All right. If you use this technique for the AP that's currently due tomorrow, it's not easy. Don't use that method. I made the suggestion there that use part A to show Jn approaches 0. That's a lot easier. It's just like 3 lines with everybody understand once it's written down. If you approach the integral method, it's going to make it very difficult to work. So I suggest use my suggestion, not this technique here. But in general, you have to approach this one like this, using the integral. So it's a complete proof. There's nothing that was hidden here. It's a complete proof to the statement that we can reach E 2.717 to that number by keep adding this number 1, 1/2, 1/6, 1/24, whatever the next one is, going like that. If you could keep walking like that, and you arrive in 2.7, and that's just an amazing formula. So if you have to program the table that you use in the calculator, and you will be using this formula to get to that. All right. So that's it.